Welcome, dynamic students. For this mini lecture, we'll be discussing rigid body planar kinematics, and we'll be discussing instantaneous center of zero velocity. This is material drawn from Hibbler's 14th edition dynamics textbook, section 16.6, and we'll be discussing this in the context of problem number 1686. So an instantaneous center of zero velocity is a point on a rigid body that at any given instant has zero velocity with respect to a fixed reference frame. So the most typical examples of this that you'll encounter are the point of contact on a rolling body, not slipping, rolling. So if you think of a wheel rolling along on the ground, the point that's in contact with the ground, if it's not slipping, if it's rolling, that at any given instant, the point that's contacting the ground isn't moving with respect to the ground. The rest of the wheel's rotating around it, but that one point's not moving. So to a certain extent, this could be called a yo-yo. It's a wheel that has two different radii, and that inner radius has kind of maybe a protrusion, and so there's this blue cord is wrapped around it. It's a double disc, so this cord wraps around the middle, and then the whole disc can rotate and the cord can unwrap. So there's old-fashioned toys called yo-yos that rely on this principle. So from the point of view of this disc, it's rotating. At any given instant, this point right here where the string is unreeling, we can look at that as an instantaneous zero velocity point, because that one point is rolling on the string to a certain extent. So the problem gives us this disk configuration, and it gives us a rotational velocity and direction. Our omega is 2 radians per second at the instant shown, and someone wants to know what the actual velocities with respect to a fixed reference frame are at points A and B. So out here on the rim, and we've got some dimensions, 2 inches for the inner radius and 5 inches for the outer radius. So the first thing that I like to do when I look at a problem like this is set up a coordinate system. And this may or may not be the most convenient one, but it's going to be as good as any. So I'm going to set up my I hat or X direction going to the right, and my J hat or Y going up, and this is going to be going down. But this allows me to say that a positive increase of theta or a positive omega or alpha, rotational velocity and acceleration, is going to be counterclockwise, which is what we have going on here. So I can write my omega in terms of something positive. So I can use my handy expression for velocity at any point on a rigid body undergoing planar motion in terms of the velocity at any other point on that same rigid body undergoing planar motion, and then use the fact that one of those points, a moving, has zero velocity. So I'm going to write the velocity of point O, which is in the middle, it's the center point of the yo-yo, in terms of the velocity here of this point, which I'm going to call V string. Because the yo-yo is kind of rolling on the string, the velocity at this point right here, the yo-yo, it's zero. This is an instantaneous zero velocity point. So I can write the velocity at point O, the center, is equal to V string plus omega, which is going to be pointing in the k hat direction, of course, because we're undergoing rigid body motion, and then crossed into R from the string attachment point 2.0. Pretty typical two velocity points in the same body, because this is a point of instantaneous zero velocity. At this instant, that's zero. We know that this is 2 radians per second, positive k hat, and we're going to cross that into a radius vector from this point back to the center, which means it's going to be in the negative I hat direction, and because the radius of this inner part of the disk is 2 inches, we can say that that's 2 inches I hat negative. So that's the same thing as saying 4 inches per second times k hat cross I hat. So we can pull out our cross product convention. K hat's coming out of the screen. I hat is over to the right. My thumb's pointing up, so that's positive j hat. Therefore, my velocity of the center is going to be equal to negative 4 inches per second j hat, which kind of makes sense because we kind of expect if we're rolling on this string, that center should be moving down. Makes a lot of sense. So that kind of passes the common sense check. So let's grab another color here and let's apply our same principle. Now we really have gotten all the information we need from the concept of zero instantaneous velocity. Now we've got the velocity of that center point. We can just use our regular relative velocities on the same rigid body undergoing planar motion to relate the velocity of point O to the velocity of any other point. So let's look at point A. We can say here's the velocity of point A. That's going to be equal to the velocity of point O plus omega, which hasn't changed. That's still our 2 radians per second. And we can cross that into the radius from point O to point A. Okay, so we just solve for this. This is negative 4 inches per second j hat plus 2 radians per second k hat crossed into the radius from O to A. Is now we're going to take this larger diameter because A is out on the very outer diameter, the larger portion of the disk. So that's negative 5 inches j hat. I go in the negative j hat direction to go from O down to A. So we're going to rewrite that. Negative 4 inches per second j hat plus, we've got a negative 10 inches per second. Write that a little neater. Negative 10 inches per second k hat cross j hat. So I'll do my cross product again. I got k coming out of the screen. I'm going to cross k into j, and I'm going to get negative I hat. So VA is going to be equal to negative 4 inches per second j hat plus 10 inches per second I hat. So it's got 2 components. It's going down and it's going, it looks like, so it's kind of got that direction, give or take. So there's our complete velocity expression for A, which was one of the things we wanted to know. we could write this in terms of a magnitude and a direction relative to a fixed point. We could use Pythagorean theorem to get a magnitude and then take the inverse tangent of rise over run. So we could do, -4 over 10. Just another way of writing it, but we can also keep it in its vector form, which I think is more convenient for what we might want to do later in the problem. Last but not least, we were asked to find the velocity at point B as well. We're going to do it exactly the same way, and I'm going to leverage point O at the center. We could use point A as the reference to find point B. That's a little bit more complicated to write the radius vector. It's much easier to use point O. So I can say the velocity at point B is the velocity at point O plus omega in the k-hat direction crossed into r from O to B, which is -4 inches per second j-hat plus 2 radians per second k-hat crossed into the radius from point O to point B is going to be, again, it's going to be in the I-hat direction, and it's going to be negative, and it's 5 inches again, so it's -5 inches I-hat. So we get -4 inches per second j-hat. We've got, again, plus -10 inches per second. Looks like that's a popular number here because the outer radius is not changed, but now we've got a different direction. We've got k-hat cross I-hat, which again is j-hat. Positive j-hat, which is going to give us a total of -14 inches per second, all in the j-hat direction. So very different, even though that's VB. So even though VA and VB are both out, they're on the same rigid body moving, they're subject to the same rotational velocity because they're on the same rigid body moving in planar motion, but because they're at different positions on that body, looking from the point of view of this fixed reference frame, this point at the top, they have very different actual planar velocities. So key concepts, what did we need to do? Basically, we needed to invoke our relative velocities on a rigid body undergoing planar motion. Our expression for that is very general to all of our rigid body planar motion discussions. And what allowed us to deploy that in this instance was to recognize that this point here was a point of instantaneous zero velocity. At the instant shown, there was the disks were not moving relative to that particular point on the string, and only to that point on the string. But that's all we needed to know because it gave us a velocity on the rigid body that we knew, and given that we knew the angular velocity of the body, that was home free. We can find the velocity at any other point. So only two pieces of information needed, but this gives you an example of the power of instantaneous points of zero velocity. You can see how if you had a wheel rolling along, any kind of rolling body, that contact point is zero. It can be rolling on a curved surface. As long as it's rolling, the contact point is always an instantaneous center of zero velocity. So things that roll relative to one another, two rolling bodies, their points of contact, provided they're not slipping, are going to be have no velocity relative to one another. So that's a very general concept that you can leverage again and again, and that gives you a point in your rigid body velocity expressions where you know something's zero. and then you can work backwards. So that basically solves for one unknown. So that is it for this mini lecture, and stay tuned for more concepts on rigid body planar motion.